Hello. In this video, I'm covering section 1.3 on the complex numbers. So let's see where the complex numbers are coming from. So suppose you want to solve the following quadratic equations. Let's consider the equation. X squared plus 1 equals 0. Okay, so if we try to solve for x, we have what? We have that x squared is -1, but the problem is that the roots are going to be the square root of -1 and the opposite of the square root of -1. So we say whenever this happens, we say that the equation has no real solution. So we need to define something called the imaginary unit. I'm going to copy this from the book, from section 2.1. But yes, we call the imaginary unit. And this is denoted with the letter I. So I equals the square root of -1. It's called the imaginary unit. This, by the way, on page 105. I'm just going to write it by hand. It's called the imaginary unit. And I squared is -1. So with that, with the imaginary unit, we can define a complex number. So if A and B are real numbers, try to make this a little bit bigger. If A and B are real numbers, then the number A plus BI is called a complex number in standard form. Complex number in standard form. Okay, so we're going to count. We have a complex number, A plus BI. And A is the real part. A is called the real part. And B, just the real number B, is called the imaginary part. Okay, so in general, this is on page 106. That one I'm just going to copy from the book. So if A is a positive number, the square root of the opposite of A is the same as I times the square root of A. Okay, so the first exercises in this section is to rewrite the square root of a negative number in terms of I. Like the square root of negative 25. This is the same as I times square root of 25. And we know that square root of 25 is 5. So we can write as I5, but most of the time we're going to write 5I. That's how we'll write it most of the time. Number 2, square root of negative 34. Now 34 is not going to be, the square root of 34 is not going to be an integer. So we're just going to keep it as I times square root of 34. And I'm going to keep it like that so there's no confusion. Whether the I is inside or outside the radical, I'm just going to keep it like that. And 3, the square root of negative 54. Okay, so this is I times square root of 54. But 54 is 9. So we can rewrite this as I times square root of 6 times 9. And we can separate the square root. So they are both positive. We can separate square root of 6 and square root of 9. But square root of 9 is 3. So this one is 3. And the answer is going to be 3I square root of 6. So I times square root of 54 is already correct, but my MATLAB will accept instead 3I square root of 6. It may not accept the square root of 54 if it's not simplified. Just be careful. With the step I did in number 3, I was able to separate 6 and 9, 54 as 6 times 9, and then square root of 6 times square root of 9 because the numbers were positive. But if the numbers are negative, we cannot use that. We cannot do that. If A and B are positive, then we cannot separate like that. The square root of negative A times the square root of negative B does not equal square root of A times B. So a short example is this one of why this statement is, of why we cannot do that. We cannot bring it together as one square root. Let's say you want to multiply the square root of negative 4 times square root of negative 9. So we cannot combine this as the square root of 4 times 9. This is instead I times square root of 4 times I times square root of 9. Or 2I times 3I. But 2 times 3 is 6, and I times I is I squared. But I squared is negative 1, so this is 6 times negative 1, or negative 6. So know that we cannot do that. So know that the square root of negative 4 times the square root of negative 9 does not equal the square root of negative 4 times negative 9. So we cannot do that when the numbers inside the radicals are negative. That one is actually square root of 36, so that is 6. So yes, we cannot bring those two together. Okay, so more examples. we will find and simplify the product or quotient. Okay, number one. That's square root of -8 times square root of -10. We're going to simplify and write in terms of I. That one is going to be in particular a real number. This is square root of I times, that's going to be I times square root of 8 times I times square root of 10. Okay, so the product of the i's is going to be I squared. So this is I squared times the square root of 8 times 10. Or -1 times square root of 80. And square root of 80, we can do something about that. This is 16 times 5. And now 16 and 5 are positive, so we can separate the square roots. The square root of 16 times square root of 5. Where square root of 16 is 4. So that's -4 times square root of 5. So the answer ended up being a real number. In B, we now have a quotient. We're going to simplify, and the final answer is, it's also going to be a real number. Square root of -15 times square root of -3. So this what I'm going to do. Square root of -15 is I times square root of 15. Square root of -3 is I times square root of 3. I will simplify this quotient. So I divided by I, the i's cancel out. $15 is 3 times 5. And we can separate the square root of 3 and the square root of 5. Okay, so this to cancel out. And the answer, the final answer is going to be square root of 5. Okay, so let's write the final answer. Okay, so that's the final answer, is square root of 5. So again, that ended up being a real number. And number 3, I was using A, B, and C. So part C, we're going to simplify the quotient square root of -56 over square root of 28. Okay, so the first two examples ended up being real numbers. This one is going to be a complex number that we're going to write in terms of I. So I'm going to write this in a way that we can simplify the denominator. This is I times square root of 56 over square root of 28. 2 times 28 is 56, so this is I times square root of 2 times 28 over square root of 28. So let's separate the roots. Now everything is positive, so we can separate the roots. And finally, the answer is going to be I times square root of 2. Or square root of 2 times I. The multiplication is still commutative with complex numbers. I'm just going to keep it like that. So you don't get the so you don't get the impression that I is inside the square root or outside so you don't get confused. Okay, so now we're doing, so now I'm doing some summations. We're going to write in the form a plus bi. Okay, so we're going to write the complex numbers. In the form a plus bi. Okay, number one, the complex number is -3 plus square root of -25. So -3, there's nothing we can do. We need to do about that. Square root of -25 is I times square root of 25. A square root of 25 is 5. So that's -3 plus 5i. 2. That's when we solve quadratic equations, we're going to see things like this, like 12 minus the square root of -48. Divided by 8. The square root of -48 is I times square root of 48. Divided by 8. These are like fractions. We can separate the terms. We can separate this as 12 over 8 minus I times square root of 48 over 8. So 12 over 8, we can reduce the fraction as 3 over 2. And then 48. 48 is the same as 16 times 3. So I'm writing in a way that we can reduce some of the numbers. This is 3 over 2 minus I times square root of 16 square root of 3 over 8, where square root of 16 is 4. So this is I times 4 times square root of 3 divided by 2 divided by 8. And finally, 4 over 8, we can simplify 4 over 8 as 1/2. Okay, the final answer in the form a plus bi is going to be 3 over 2 minus I times square root of 3 over 2. Or sometimes you may write this already correct. But sometimes you may see it as 3 over 2 minus I times square root of 3 over 2, and they are both correct. Either way, the answer is correct. Well, actually, I should leave it like this. So I'm going to uncircle this because we wanted the answer in the form a plus bi or a plus ib. Yeah, so I'm going to leave the second answer. So we have a plus bi. Or you can write like this if you want. If you are picky about the order, I mean, the multiplication is still commutative with complex numbers, but you're picky about the order, you can write like that. Okay, the next part is going to be the arithmetic, the addition and subtraction of complex numbers. So there's a couple of formulas, but really there's no need to memorize those things. That's like basic algebra. We just combine like terms. So this on page 108. For complex numbers a plus bi and c plus di, we add complex numbers by we add and subtract complex numbers by combining like terms. So really, there's no need to memorize these formulas. So if we want to add 5 plus 6i, plus 3 minus 7i, so we just combine like terms. We can remove parentheses and then combine like terms. Where 5 plus 3 is 8, and 6 minus 7i is 1i or simply I. Number 2. (3i) plus -2 minus 4i minus -5 plus 7i. Okay, so we can distribute the minus sign and drop the parentheses. That's 3i minus 2 minus 4i, and then plus 5 and distribute the minus 7i. And then combine like terms. So the real numbers are -2 and 5. -2 plus 5 is 3. And 3i minus 4i is minus i. Minus i minus 7i is going to be minus 8i. So this is just basic algebra. When multiplying, they also give you formulas, but there's no need to memorize the formula. We're just going to use, we're just going to FOIL and use the fact that that I squared is -1. So this is still on page 108. Okay, so they give you this formula, but you're not going to memorize that. All you do is basic algebra, you just FOIL. So that is the product of the first ones is AC. The product of the outer numbers is ADI. The product of the inner numbers is BCI. And the product of the last terms is BDI squared. But I squared is -1. So this is AC plus ADI plus BCI minus BD. And if we separate the real part and the imaginary part, the real part is AC minus BD. The imaginary part is AD plus BC. Okay, some examples with multiplications. We're just going to do basic algebra. We're not going to try to memorize any formula. So math, it's I mean, sometimes it's not necessary to just memorize a bunch of stuff. So multiply 3i times -4 plus 5i. So what we do is go to distribute. 3i times -4 is -12i. And 3i times 5i is going to be 15i squared. But I squared is -1. I squared is -1, so this is minus 15 minus 12i. Number 2. Uh, 3 minus 2i times 4 plus I. Okay, so we're just going to FOIL. The product of the first terms is 12. 3 times 4 is 12. Outer terms, 3 times I. Inner terms is the product is 8i or minus 8i. And 2 minus 2i times I is going to be minus 2i squared. Where I squared is -1, so that's 12. 3i minus 8i is minus 5i plus 2. And final answer is 14 minus 5i. Number 3. We have two complex numbers with equal real parts and opposite imaginary parts. So if we do this by FOIL, we can treat this like a different, like the product of the sum and a difference. And we know from basic algebra that this is the difference of squares. If we just FOIL, that's going to be 25. And then 5 times minus 4i, 4i times 5, and 4i times -4i. So that's minus 16i squared. So the minus 12i plus 20, minus 20i plus 20i, they cancel out. I squared is -1. And the final answer is 25 plus 16, or 41. So the answer ended up being a real number. So those type of numbers, and I'm going to mention this, those type of numbers where that have the same real part but opposite imaginary part are called complex conjugates. And number 4, we have the square of a binomial. So the square of a binomial, that's going to be the square of the first plus 2 times the first times the second times the square of the second. So this is 4. 2 times 2 is 4. 4 times 7 is 28. 7 squared is 49 times I squared. So this is 4 plus 28i minus 49, or negative 45 plus 28i. Okay, so the example 3 was an example of complex conjugates, where we multiply the numbers, two numbers with same real part and opposite real parts, and the answer ended up being a real number. So that's on page 109. And the example that we did was 5 plus 4i and 5 minus 4i. The answer was 41 because this 5 squared plus 4 squared, or 25 plus 16, which is indeed 41. So that will allow us to write a quotient of complex numbers in the form a plus bi. Okay, you have something like, so all we need is the conjugate of the denominator. If we have something like 2 divided by I, we can multiply, in this case, the conjugate of I is going to be the opposite of I. We multiply by that in the numerator and denominator because multiplying the same thing at the top and bottom preserves the equality. And that's going to be minus 2i divided by minus I squared. But I squared is negative 1, so this is minus 2i divided by the opposite of negative 1, or negative 2i. So 2 over I is the same as 2i. For something a little bit more complex, or more complicated, something a little bit more complicated than 2 over I, let's say you want to write 4 plus 5i over 1 minus 2i in standard form a plus bi. So what we're going to do is use the conjugate of the denominator. So 4 plus 5i over 1 minus 2i. If we multiply the same thing at the top and bottom, we preserve the equality. We preserve the equation. The conjugate of 1 minus 2i is 1 plus 2i. Okay, so that is going to be 1. That's going to be, so this is 1 squared plus 2 squared. I'm using the formula that we saw that I copied. That's going to be the sum of the squares of the real part and the imaginary part. And then we have on top 4 plus 5i times 1 minus 2i. So this is 1 plus 4. And then FOIL, this is 4, or 4 times 1, 4 times 2i, 5i times 1, and 5i times 2i. So that's going to be 10i squared. the denominator is going to be 5. And then we have 4. 8i plus 5i is 39. And 10i squared is going to be minus 10. We're almost there. 4 minus 10 is negative 6. And finally, to write in the form a plus bi, we're going to separate the terms. This is minus 6 over 5 plus 13 over 5i. Okay, so that is the final answer. So when we have a quotient, we're going to when we have a quotient and we want to write in standard form a plus bi, we can do it by using the conjugate of that number. Okay, notice the following pattern. We know that any number to the 0 power is 1, or any non-zero number to the 0 power is 1. Any number to the first power is itself. We saw that I squared is negative 1. And I cubed is going to be, you can separate this as I squared times I, where I squared is negative 1, so that's going to be the opposite of I. Okay, next, I to the fourth, this is I squared times I squared, where I squared is negative 1. So I to the fourth is 1. I to the fifth, this is the same. So I to the fifth, you can write this as I times I to the fourth. And we saw that I to the fourth is 1. So that's going to be I times 1. Or simply I. I to the sixth. This is I squared times I to the fourth, where I squared is negative 1, and I to the fourth is 1. And I to the seventh, it's I cubed times I to the fourth, where I cubed is the opposite of I, and I to the fourth is 1. Okay, so in general, we're going to have this pattern of 1, I, negative 1, minus I. And that will keep repeating. So we have one cycle, then the next cycle is also going to be 1, I, minus 1, minus I. And that will keep repeating. So we can use this to simplify powers of I. Well, that's actually 1. If you do I to the 23rd power, you can rewrite. Okay, so since I to the 4th is 1, we can write this in a way that the power is a multiple of 4. So we can do something like I to the 20 times I cubed. So I'm doing this because I to the 20 is I to the 4th to the 5th power. I to the 4 is 1. So this is 1 to the 5th power. And I cubed is the opposite of I. So the final answer is going to be minus I. And number 2, we can do this if we have negative powers as well. You have I to the negative 3. Okay, so since I to the 4 is 1, and multiplication by 1 gives the number as it is, we can multiply by I to the 4. And I cubed is the same, or I to the negative 3 is the same as I to the negative 3 times I to the 4. Okay, so properties of exponents, those are still applicable. That's I to the minus 3 plus 4, and that's going to be I to the first power, or simply I. So yes, any power of I, positive or negative integer, is going to be one of those four. It's going to be 1, I, minus 1, or minus I. And I'm going to finish this section with an application. So if you're wondering whether this is applicable to real life problems, the answer is yes. Most of the applications are beyond the scope of college algebra, but I'm going to show you an application to electric current. So I'm not going to go over the details, but yes, complex numbers are applicable to real life. So complex numbers are used to describe the current I, voltage E, and impedance Z. These three quantities are related by the equation E equals I times Z, which is known as Ohm's law. Thus, if any two of these quantities are known, the third can be found. In each exercise, solve the equation E equals I times Z for the remaining value. So we're doing number 88. That's on page 112. Just to show you that complex numbers are indeed applicable as real-life models. Okay, so we know E and Z. We are going to find big I. So set up the equation. And capital I times 9 plus 5i is equal to 57 plus 67i. This means that I is a quotient of complex numbers. So we're going to write this in the form a plus bi. We can do that by multiplying by the conjugate of the denominator. Multiply top and bottom by the conjugate of the denominator. The denominator is going to be 9 squared plus 5 squared. The numerator is going to be what? It's going to be 57 times 9. We're foiling, then 57 times minus 5i. Then 67 times 9 I, or 67 9 times 9. And 67 times minus 5I. Okay, we're almost there. The denominator is 81 plus 25. At the end, that's going to be 106. Then, so this 513. Then 285I plus 603I. This is 389. And 335I squared, that's going to be plus 335. So 513 plus 335 is 848. Over 106. We're just going to separate the terms and write in the form A plus BI. This is 848 over 106 plus 389 over 106. But 848 over 106 is, that's going to be 8. And 318 over 106 is 3. Okay, so this is it. Okay, just making sure, yeah, everything is positive. So yeah, this is it. So we're going to stop here. Thank you for listening.